So for the first one, we're going to be multiplying everything in the first parenthesis by everything in the second parenthesis. When it says expand, it means multiply it all out. So I'm going to have to do the x times x first. That gives us x squared. Then we do the x times the minus 3. So that's going to give me minus 3x. Then I do the same thing with the 8. So 8 times x, so that gives me a plus 8x because it's positive. And then we do the 8 times the minus 3. 8 times a negative 3 is a negative 24, so it's minus 24. Now it did say to expand it, and that is certainly expanded, but there's an inherent unstated rule that we always have, which is to always simplify if we can. And can this one be simplified? Yeah. We can combine like terms in this case. Now, the like terms do not include the x squared, however. That is the only term that has the x being squared. But the negative 3x and the 8x, we can combine those. So negative 3 plus 8 is going to give me 5, so that's going to be plus 5x. And then minus 24, because there's nothing that changes the 24 there. Use that example if you weren't sure how to do the rest. Use that example. Go ahead and now go through the rest of them. Keep going through. All right, so I'm going to start working number 2 now so you can follow along and make sure you got that one right. So for number 2, you should have gotten 2x squared minus 9x minus 5. And then when you go to do number 3, remember squaring means multiplying it by itself. So the first thing you want to do on number 3 is rewrite that as 3x minus 5 times 3x minus 5. Exponents do not distribute, so we can't simply square each of the terms on the inside. Right, then once you've written it out that way, you can go ahead and then multiply them together. After you multiply it out and combine your like terms, you should end up with 9x squared minus 30x plus 25 for number 3. Now, when doing number 4 is a little bit of a different beast because you got that 3 hanging out front. So, the question is, when do we put in the 3? And actually, it depends. The one time when you can't put it in is you can't put it in before squaring. So the very first thing we have to do is we have to write it out as 3 times x plus 4 times x plus 4. You now have 2 options about what to do with this. You can either multiply the 3 into the parentheses, in which case if you do that, you multiply it into one set of parentheses only. If you multiply it into both sets of parentheses, you just multiplied it in twice. So you multiplied everything through by 3 times 3. We're only multiplying 3 once. So it could go into one parenthesis, or you can multiply the 2 sets of parentheses together, and then after that, deal with the 3. The latter is the one that I find the easiest usually. So that's the one I'm going to go ahead and demonstrate up here. So if we do that, the 3 is just going to hang out front for the time being. And now I'm going to multiply the x plus 4 times x plus 4. And so we end up with 3 times x squared plus 8x plus 16. Then I'm going to go ahead and multiply in the 3. So now when I distribute in the 3, I end up with 3x squared plus, now I do the 8 times the 3, 24x plus, now the 16 times 3, 48. And then that gives us our final answer. So you're now going to factor these. And it's basically what we just did, except backwards. And you've actually already been practicing this a decent amount. You've seen a lot of it on WAMAP even, where you're asked to factor a quadratic. The big thing to remember is we are adding to the middle number, and we are multiplying to the last number. So if you're going to do number 1, you're saying what 2 numbers add to 5 and multiplies to 6. When you find them, then you can write your factored form. Okay, so we'll check in there on number 1, see how well you've done with that. The 2 numbers that add to 5 and multiply to 6, 2 and 3. And so our factored form here is x plus 2 times x plus 3. Hopefully you notice some connection between this and the previous set of problems that we just did, because when we were expanding them, we saw how whenever we multiplied these two together, we got the last number. And this middle term, when we were doing those previous problems, came from doing the 2x plus the 3x. We ended up adding those together to get that. All right, so then number 2. Again, we're saying what adds to the middle number multiplies to the last number. Sometimes this one can be a little bit tricky for us because we tend to end up with a little bit of a blind spot for this particular combination. Because we spent years of people saying, okay, what can we divide this by other than 1? But 1 and 9 is actually the combination that we want in this particular case. So it ends up being negative 9 and positive 1 to add to negative 8 and multiply to negative 9. Number 3, add to negative 16, multiply to 64. That ends up being negative 8 and negative 8. But I don't really want to leave my answer like this. The x minus 8 times x minus 8. We want to write this as succinctly as possible, and I can write that a little bit more succinctly, a little bit shorter. So rather than x minus 8 times x minus 8, since it's multiplied by itself, I can write it as x minus 8 squared. And so we're just going to take that one extra little step there and make that into x minus 8 squared. Yes, when you're doing the wall map problems, you will need to be that specific. I specifically told it to be that precise and that picky because I need you in the habit of writing it that way. Partly because as we get into some later stuff, we're solving some of our quadratic equations. By doing it this way, it actually is going to allow you to solve some things which otherwise might not seem as easy to solve if you wrote it separately. All right, number 4 now. If you're having trouble with number 4, take a look back at the last set of problems, number 4. Back there, we ended up with an answer that looked a lot like this one. And in order to get there, remember we had that number out front. This one, we actually want to start by figuring out what that number out front could be. What can I divide 2, 20, and 48 by? 2. So I'm going to start by doing that. Since I'm dividing it by 2, I'm going to write that outside of the parentheses because I still need it equal to the same thing. And then I divide everything through by 2. Notice this still equals the same thing as what we started with. It's just written in a different form. But if I distributed it into 2, I'd get what I started with. But the reason why I want to do that is because now notice that I'm just starting with a plain old x squared. When it was a 2x squared up here, I couldn't use the same old add 2 multiply 2 rule. But now that this is just a plain old x squared, I can. So now we can say what two numbers add to 10 and multiply to negative 24. That 2, it's just going to hang out front. It's going to stay there, no changes. Basically, you just carry it down each step along the way. I'm multiplying to a negative 24, so that tells me that one of my numbers has to be negative and one of my numbers has to be positive. And then, what are those two numbers that multiply to negative 24 and add to 10? Negative 2 and 12. Now, if you're looking at it and you're thinking about 6 and 4, very close, but the only way 6 and 4 would give us 10 is if they were both the same sign. And in this case, since we're multiplying to a negative 24, the two signs have to be different, because that's the only way you multiply to a negative, is one positive, one negative. In order to start looking at graphing, I'm actually going to have us start with this problem. So please start on your own paper by graphing y equals the absolute value of x minus 6 minus 8. All right, so this is what you should end up with for our graph here. So a little bit of a reminder, how do we put this together? Well, the minus 6, that is inside with the x. Since it's inside with the x, that tells us that it's going in the x direction, left and right. This is the one that tends to be opposite of the way we'd naturally think. Minus goes to the right. The minus 8, hanging on the end. It is on the end, it's not in with x, therefore it's going up and down. This one happens the way you think it should. Minus 8 goes down 8. So the very first thing I did is I went right 6, down 8, plot a point right there. Quick review. What do we call that point? Yep, some of you got it right there. That is our vertex. Yep, that vertex, it tends to be our starting point here, but it's also known as the highest or the lowest point on the graph. So we start by plotting the vertex, and then since this one is absolute value, that is, we know it because we got these absolute value bars around it, because it's absolute value, then we know that it's going to be a V-shaped graph, and so we go over 1, up 1 on both sides to finish it out. A little bit more review. What is the range of this graph? Now, if you don't remember that range is a description of what possible y values appear in the graph. Yeah, our range here is that y, because we're talking about the possible y values with range always, are greater than or equal to -8. Because as we take a look at this graph, our graph starts down at -8 in terms of the y values and includes everything above it. So that's our range, y greater than or equal to -8. We're going to be extending our knowledge that we have from absolute value to y equals x squared today. This is going to be our new graph. This is a quadratic. It's the actual name given to any type of equation that has the x squared as its top end. So we're going to be going ahead graphing this. Since we're going to graph it, go ahead and set up a graphing grid on your own paper there, and set up a little table there where you can write these points as well, so you're ready to go as we do it together. Alright, so we're now going to fill in the table and figure out what the points of this graph should look like. This is the only time we should have to actually make a table for this graph. Every time you go to graph one after this, you're going to know what the shape is, you won't have to make a table. Alright, so when making our table here, I always like to start with a nice simple x of 0. So if I plug 0 into that equation for x, then I'm doing 0 squared, and 0 squared equals 0. Because squaring something is multiplying it by itself, and 0 times 0 is 0. So that gives me a point that I plot, 0, 0. Okay, what if x is 1? What's 1 squared? 1, because 1 times 1 is 1. Alright, so far this is exactly the same as our absolute value, but that's about to change. What if x is 2? What's 2 squared? So I got the point 2, 4. So notice this is where things start diverging from our absolute value graph that we had before. Alright, let's keep going here then. If x is 3, what is y? It's 9 because we're doing 3 squared. So that gives us the point 39. Okay, what if x is 4? If x is 4, then y is 16. Alright, so 4, 16, that's off my graphing grid. Might not be off yours, I don't know, but it is off of mine, so I'm not going to worry about plotting it. Since that's out of bounds for me, I'm not going to worry about putting any others in the table at the moment. But just realize that the table does continue on with lots more points if they fit on your graph. So it would also include, for instance, 5, 25, 6, 36, 7, 49, and so on. We're just squaring our x values to get our y's. Alright, so I know what's happening 0 and up. What's happening though on the left side? We got to check our negatives. So if x is -1, what's -1 squared? Well, -1 squared means -1 times -1, and a negative times a negative is a positive, so yes, it is 1. So I got the point -1, 1. The rest of these should go pretty quick then. -2 will give us 4. -3 will give us 9. And -4 will give us 16. Anytime you square a number, it'll always be positive. That is a rule that is true 100% of the time with real numbers. So you plot those points, then this is what you should be looking at for a final graph after you put it all together. Now there is something in particular that I want to show on this graph. if we take a look and see what's happening all the way down the middle here, I want you to note that our graph is actually leveling out down in here, because as you get to smaller and smaller numbers, when you square a number that's less than 1, it gives you a number that's even smaller than you started with. And so our graph is actually leveling out here. It doesn't make a sharp edge V like the absolute value did. It's a smooth curve that levels out when it changes direction. So the entire graph is a curve. There's not a straight bit to it. And so check to make sure that you are getting that result. What's the range of y equals x squared then? This is our parent function. What's the range? Well, it's values that are greater than 0, yes. So it's greater than or equal to 0, because it actually does hit 0. And what is greater than or equal to 0? Y. Because range is always talking about our y values. So our range for this one happens to be y is greater than or equal to 0. Of course, that can change if we move the graph. Having graphed y equals x squared, you now actually already have all the tools to be able to graph this. Y equals x minus 6 squared minus 8. Because our graph here of x squared operates the same as the absolute value of x. The minus 6 is going to do the same thing it did with absolute value. The minus 8 is going to do the same thing it did with absolute value. All right, in order to make this graph, just like with our absolute value, we go right 6, we go down 8, and plot our first point. From there, we're plotting the points the same as we did with that parent function. Just in this case, it's all relative to that first point. So you notice from that vertex point that I plotted, it is then over 1 and up 1. That's that point 1, 1. Then we have the point over 2, up 4, because 2 squared is 4. Okay, over 3. 3 squared is 9, so it goes over 3, up 9. Notice it's all relative to the vertex. It's not relative to the last point that you plotted, but rather to the starting point. And that's the easiest way to make that graph. You could theoretically take all the little individual points, like take 1, 1 and move that one right and down all separately, but it's a lot easier to just figure out where that starting point is and then use the same table all relative just to that point. All right, so now let's actually take a look at a comparison of the two graphs that we've done here with the same transformations. Both of these were x minus 6, and both of them had a minus 8 hanging on the end. It's just the first one that we graphed today was absolute value, and the second one we graphed today was x squared. So what is the same and what is different about these two graphs? Well, what all is the same? The vertex is the same. Yeah, excellent. And that's a super important one. The vertex being the same means we don't have to learn a new way to get the vertex. I like it when something transfers over directly. All right, what else is the same? Yeah, 1, 1's the same, right? In fact, really, there's 3 points that are the same, right? We got the points, that starting point of the vertex, and then there's the over 1 and up 1 on both sides of it. So we got 3 points then that are the same. Okay. What else is the same? Well, there's one other thing we've talked about today that should be the same between them. How about the range? The range is the same, right? Because since they both have the same vertex and they're both going up from there, they both have the same range. Okay, so then what's different about these two graphs? Yeah. Slope. See, that's a big one right there, is slope. Because slope is actually a great way to talk about our absolute value graph, right? Because it's over 1, up 1, over 1, up 1, over 1, up 1. It's got a constant slope of 1 on that side, -1 on the other side. But slope takes on a different meaning when we start looking at quadratics. Because with our quadratic, we go over 1 and up 1. Then we go over 1 and up 3. Then it's over 1 and up 5. This does not have a constant slope. And if we're talking about slopes, really we are looking at something that is constant. And so slope is a huge difference between these, because when we talk about absolute value, we can talk in terms of slope on each side. But when we talk about a quadratic, slope is a meaningless concept. Slope doesn't help us when we're graphing a quadratic. Instead, we have to rely on some other means and other language to be able to talk about it. So slope, yeah, huge difference. What else is the difference between these two graphs? Well, the slopes are different because the shapes are different, right? So, of course, the shapes are different. We got to include that part. All right, so there is now one other similarity I want to bring out for you. And that is something we haven't talked a lot about, but you notice that both of these graphs are actually symmetrical on both sides of the vertex. So it's going to be the same on both sides of that line. They both have that same symmetry. And I want to talk about this symmetry a little bit because it's actually a bit of vocabulary and a bit of activity that you should be able to complete. This line is called the axis of symmetry. And you will at times be asked to tell me where is the axis of symmetry for a given graph. When you do that, this is what it's looking for. It's looking for the equation of that dotted line that I've drawn there. Now, what is the equation of that line? A lot of times I'll say, what's the axis of symmetry? And somebody for this problem would tell me 6. If I gave you just the number 6 and asked you to graph it, you'd probably start getting very confused. We can't graph just a number. In order to make a graph, we have to have an equation. We have to know what 6 equals. If it's going to be a vertical line, it then is x equals 6. And so if you're ever asked for the axis of symmetry, it is going to be x equals that number. And that number is always the x-coordinate of the vertex because the axis of symmetry will always pass through the vertex. All right. I'd now like you to make 3 new graphs. Do each one on its own separate set of axes. All right, so here's your graph of y equals negative x squared. Notice what the negative is doing here. It's doing the same thing it did with absolute value. That negative out front reflects it across the x-axis, meaning that instead of going up, you're going down. The over stays the same. And you're still going down by the same amount that you went up. So notice it's over 1 down 1, over 2 down 4, over 3 down 9, same thing that you had done before. Now, one thing I do want to deal with though here, because sometimes the question comes up, wait, if we square a negative, doesn't that give us a positive? So shouldn't this be the same? That would be the case if we had parentheses around the negative x. However, without those parentheses there, what it's actually saying is square the x and then multiply it by -1. That's really what that means. It's just been shortened up a lot, so we tend not to necessarily see that subtlety in it. And so we got to do that exponent before the multiplication, so square the x and then apply the negative to it. All right, here's what our graph of x minus 3 squared would end up looking like. The -3 is in with the x, so it moves it in the x direction. And just like with absolute value, a minus will go right, a plus would have gone left. So we start by putting our vertex right 3, and then from there we follow the same pattern we do every time we graph x squared. Over 1 up 1 from the vertex, over 2 up 4 from the vertex, over 3 up 9 from the vertex, and so on and so forth. One little detail-y thing, because it seems like a good time as any to mention it. A few little details with vocabulary. Remember that any time we are dealing with an equation where it's gone up to x squared, we call that a quadratic. When we graph a quadratic, we get this U-shaped graph. That U-shaped graph also has its own unique name that we'll be using here and there. It is called a parabola. So that's our parabola.
I remember.
Yep, many of you probably have seen that before.
I did it right.
So the plus 5, in this one, x squared plus 5, it just moves it up 5. So again, we plot where that vertex goes up 5, and then we follow that same pattern from there. Over 1, up 1, over 2, up 4. And really that's about all that fit on the grid in this case. Alright, so you graph this one now on your own paper as a way to check and make sure that you're on the right track. Let's see how you've done with it. So, we've basically taken each of the 3 things that we had done individually in the steps before, and we put them all together in one. So notice the transformations and what we say for them. The negative is a reflection across the x-axis. And we also want to say that it is shifted right 3, and it is shifted up 5. When making the graph, basically we want to have these 3 in mind. If looking at the equation with all that stuff going on ends up overwhelming you, write out the transformations first, because it gives you basically step-by-step instructions of all the things you actually have to worry about. I always deal with the shifts first, so we go right 3 and up 5, put your first point there at your vertex, and then from that point we're going to follow the same pattern that we always do, just we're going down instead of up. So over 1 down 1, over 2 down 4, over 3 down 9, over 4 down 16, if it fits on your particular graphing grid as well. And then finally, what is the range of this particular graph?
Ooh, I got it. X is less than or equal to 30?
No.
No?
Because range is dealing with y.
Oh.
So it's y.
Y is less than or equal.
Less than
No,
or equal
greater-
to
yeah,
5.
5.
Because we're saying what y values does this include? It includes all y values below that line at 5. So it's going to be 5 and down from there for our range. So that's why we'll say y is less than or equal to 5.